Right. So this is what we have seen so far of our sort of summary of the PML theory. Right. Conclusion was that just by changing the coordinate stretch parameters, I can mimic a lossy medium with 0 reflections. That was our conclusion. One thing I wanted to point out, that in this derivation that we did, we assumed a time convention for in this derivation of e to the minus j omega t, right. So, our time convention was e to the minus j omega t. This led us to choosing our s of the form p plus jq, right, because it is e to the minus j omega t. So, the space term has a plus jkx, right. Now, if I were to have the opposite time convention e to the plus j omega t, then my s would be p minus jq. Okay. So, these are some of the very simple implementation issues you should keep in mind, otherwise you will find that nothing works in your code. Okay. Alright. So, what we have discussed about PML so far is independent of how I will implement it, right. So, finally, after having done all of this theory, the payoff is how do I actually implement it in my method. So, that is what we are going to talk about next, right. So, implementing it into FDTD, and turns out it is actually very simple, just depends on us looking at Maxwell's equations a little bit differently. Why? Because that coordinate stretching parameter, it appeared in Maxwell's equations just by relooking, right. So, again a simple relooking is what will help us. So, let us do a little bit of a trick. Okay. So, our usual Maxwell's equations, let us just rewrite them in a way that is useful. So, for example, the curl of H, right. So, let us expand it out. So, the x hat component, what all terms are going to be there? That is the first term. Okay. Then I have a y hat term, which is y by h x z minus h z x, and then I have a z hat component which will have a d by dx h x d by d. Right. This is the usual way in which we write the curl, right. Now, if you remember when we had redefined our Maxwell's equations, we had got these coordinate stretching parameters. Were they accompanying the x hat, y hat, z hat, or were they accompanying something else? When I redefined del to del E or del H, how did I redefine those? Yeah, but it accompanied which term? The partial derivatives term, right, not the unit vector terms, right. So, for example, so what I can do from here is extract out the common partial derivative terms. Okay. So, to see that, let us have a look at one other thing. So, supposing I ask you what is x hat cross h. Okay. So, x hat cross h will be what do I get from here? So, there is only a z hat and a y hat, right. So, z hat is going to be h y, and I am going to get a minus y hat h z. Okay. Do you recognize a term like this up here somewhere in the expression above? Does this sort of appear somewhere? What is I mean, yeah, so what is common to these guys? So, what is common over there? The partial derivative with respect to x, d by dx is appearing everywhere here, right. So, I can rewrite this like this. So, curl of h I can rewrite now as del by del x, x hat cross h, then that takes care of the del by del x terms. Then I will have what? Del by del y, y hat cross h plus del by del z, z hat cross h. Okay. No approximations, this is just rewriting. So, over here it was written in terms of the unit vectors x, y, z. Now I am rewrite, so this is unit vectors, and this is in terms of, I have grouped the partial derivatives. Right. So why do I do this? Because this is now in a form that my coordinate stretching will give an easy interpretation. Coordinate stretching will just multiply the del by del x by a 1 by HE, I mean 1 by HX or 1 by EX term, right. So this is allowing us to see that. Now, so let us look at, for example, to make the implementation into FDTD, we will use something which we already know, which is how to deal with lossy media. Okay. So let us just put this equation 1, we will put it on hold and we will see the comparison next. We will look at lossy media and we will use something very simple, we will use our Ohm's law. Okay, we have already done that before. Ohm's law is J is sigma E, right. So over there what did I have? So curl of H gave me J plus dd by dt, we know this, and this became, so dd by dt, so this gave me sigma E plus J omega epsilon naught epsilon r E, right, which I rewrote in, I can write this in terms of a complex permittivity, right. So I can write this as J omega epsilon naught common epsilon r, then minus J sigma by omega epsilon naught E. So this we have already seen, you can call this as epsilon prime. Okay. So you might have guessed why we are taking recourse to a lossy media, because we have already given the interpretation that PML with coordinate stretching is like a lossy anisotropic media, right. So we can use something that we already know towards over here. Okay. So now curl of H by Maxwell's equations is going to be equal to, so I have this relation over here, I can now use this equation 1 that I have written over here, right. So all of these terms accompanying the electric field are scalars, right. So this vector over here, will you agree that each of these 3 terms is a vector, right. The direction is not clear, I mean it depends on where H is, right. So I can rewrite this whole thing in terms of 3 vectors like this, okay. I can write this as E Sx Sy Sz. So what am I saying? I am saying that equation 1 has 3 vectors, right. It has 3 vectors, each of these terms is 1, 2, 3, each of these 3 is a 1 vector, right. And curl of H finally by Maxwell's equations is going to be equal to this term. The electric field also has 3 vectors, so I am defining these 3 vectors. So E Sx, for example, what is the definition? This is a new definition I have introduced. This will be equal to 1 by j omega epsilon naught epsilon prime by definition, okay. This is my definition. Can I do that? So I have decomposed the electric field into 3 vectors, Esx, Esy, Esz. So good point. So these vectors Esx, Esy and Esz, they are not along x hat, y hat, z hat. They are not. They are along 3 arbitrary directions. What are those 3 arbitrary directions? They are given by the unit vectors x hat cross h, y hat cross, right. I can decompose a vector into any 3 orthogonal directions as I want. So these are not along x hat, y hat, z hat. 3 arbitrary directions which are defined as x hat cross h, y hat cross h, z hat cross H. Okay. So far I have not done anything new except just reinterpret Maxwell's equations and lossy media, right. There is no mention whatsoever of PML. Okay. So now next is we will look at how to implement PML. So can you anticipate what will happen?